Awesome. So, yeah, welcome to the monthly paper reading group of Merantix Momentum. This is, an event by one of the ventures of Merantix, who sits here and has also founded the AI Campus and Merantix Momentum. We are essentially does two things. So we are have an engineering consultancy helping small to medium-sized enterprises to sort of adapt machine learning and make it work in the real world for their use cases. And then we have a research department that stays up to the latest research papers and also tries to contribute back to the research community in the form of papers and visiting conferences, etc. And today I'm very happy to say hi to three of our engineers who run part of the client business, and they traveled to the EMNLP conference, which happened in Abu Dhabi in December. And this conference is really considered one of the best in the field, and we're really happy that some of our engineers can travel there and then come back with some of the exciting information that they found out about there. Perfect. I think so far so good in terms of the introduction. Just one thing: this event will be recorded, so and later it'll be uploaded to YouTube. So yeah, just so you know, if anyone's not fine with it, I'm sure we can find a solution also. Otherwise, I will say the goodbye note. Please feel free to ask questions in between, and I'll also try to monitor the chat a little bit so we can see what's going on online. Wonderful. Then I would like to hand over to Peng, and the stage is yours.
All right. Hey everyone, I'm Peng. I'm part of the NLP team. And together with my colleagues, we traveled to Abu Dhabi for the EMNLP conference. And I would like to share you some insights, some questions we had. And let's start with some pictures of us at the conference. Abu Dhabi is quite an interesting place. We had a party there with the Grand Mosque in the background, and absurdly, it only rains once per year, and it rained on that party, and everyone got wet. And But I want to start with the summarization of a workshop that I found quite interesting. It's kind of a niche topic. And it's about emergent communication. So what can we imagine under that? It's basically like studying how neural networks would communicate, in the sense that there are, for example, two neural networks and they have to solve a task, for example, a cooperation game. And in order to solve that task, you need to communicate. And what kind of communication protocol would emerge under this circumstance? This is what this field is studying. And it might be interesting to see, like, are there actual parallels to how humans and animals communicate? Can we learn something about how human language emerged naturally? Or can we use that insight from the study to, for example, improve how humans can interact with machines? And in a very basic setup, so I think most of the papers in this field experiment with this, what is called a referential game. You can imagine this game with, for example, one agent. It sees, so this agent needs to repair a car, and it gets an input, an idea that it needs a screwdriver, but it needs to somehow communicate to the other agent to fetch the screwdriver. And they don't know how to speak at all. They can just exchange some discrete symbols, but they need to figure out what kind of symbols they exchange in order for the other agent to fetch the screwdriver. instead of the mojito or a tile. So to summarize, in this kind of game, you would have a sender and receiver. And the sender would get the input, for example, the image, and will send a message to the receiver. And those messages are discrete. There's really no supervision on how those symbols or how this communication should look like. And it would naturally emerge because we only kind of use the reward from completing the task. So if you have any questions, just pop in and ask. And so in the earliest works, this is exactly what they're doing. It's a pretty simple setup. You would have, the sender would get two images. One image, let's say this image of the dog is selected to be the target image. And the sender needs to communicate this to the receiver through some discrete symbols. Let's say those three symbols. This receiver will get this message and would need to select among those selection of images the target image, which is this dog. And the architecture is pretty simple. You just use some pre-trained image encoders, and on top of that, you have a feed-forward network. And the sender will just sample some symbols, send it to the receiver. The receiver will combine this message together also with some pre-trained embeddings in order to compute, okay, which image is the sender actually referring to. And this worked out quite well. So the receiver almost always selected the right image. And but we can also ask ourselves, okay, those symbols, do they actually refer to the actual concept? So if he says symbol 1, does he really refer to a dog or just some, I don't know, random noise? And here you can see this plot where each dot, each point is basically embedded, is like the visual embedding plotted in this 2D space. And like two dots are close if they visually describe a similar symbol, a concept, like an alligator here. And the color encoding means what kind of symbols were used to describe this. So you can roughly see the points that are closer together also have the similar color encoding. That means like visually similar things also use the same symbols. And like roughly you can also say, okay, those blue symbols, the symbols encoded with blue, they roughly describe living objects. And those green symbols, they roughly describe non-living objects. And they say, okay, this is also quite similar to how humans like would naturally evolutionarily have developed the language. That's because there's like such a basic distinction between living and non-living. But we can't be too happy too early because later on some follow-up papers showed that actually if you train agents to play this referential game and they do it pretty well, but at test time, instead of showing real like images about dogs and cats and like real concepts, you let them talk about blobs of noise, Gaussian noise. Would they still like perfect this game? Can they still talk about this kind of stuff? It seems like, yeah, they can like use those symbols to distinguish this left Gaussian blob of noise from the right blob of noise, which kind of means like they don't really refer to like meaningful concepts when they use those kind of symbols. Instead, they might use some random low-level pixel information. Another thing they have looked at is, okay, so human language kind of have this kind of efficient encoding where the most frequent words, they are pretty short, like the top most frequent words in English, like the, of, and, to. And the top 10 most rarest words are pretty long. And this is called, in linguistics, I think, called the Zipf's law of abbreviation. And they want to find out if this law can also be observed when neural networks communicate with each other. And here you can see on the y-axis the message length, on the x-axis how frequent these symbols occur. And you can actually see in this emergent language, we would actually have an inverse relationship. So the things that are quite frequent are actually encoded quite in a long length. And but if you look at the natural language like Arabic, you will see this Zipf's law of abbreviation. And in the green line, you can see the optimal encoding on the information theoretical basis. But if you like explicitly penalize that the message length should be short, then you get this yellow line, I guess. Still, it shows a similar trend to the Zipf's law, but it's not nearly as efficient as like natural language like English or Arabic. So far, these were pretty early works, and they used pretty. They didn't use a lot of concepts where the neural networks need to distinguish from, and also those visual encoders were pre-trained. And these guys, they thought, okay, let's just make it larger, have much more concepts where there's the neural networks need to distinguish, and also train those visual encoders from scratch and see what happens. So the setups you can see here is also quite similar. So you would have a target image gets encoded. There's a symbols generator which generates these messages, and the receiver will receive those messages and try to distinguish from the set of candidates which message the sender has seen. And they compare it to unsupervised representation learning, because in some way it's quite similar. Because, yeah, why is it similar? Because, well, you would basically, the only difference I would say is that in this symbol generation phase, you have discrete stuff. And yeah. So this is the performance of how successful this communication game played out. How many times the receiver was able to pick the right image. So in this column on the validation set, you can see it performs quite well across those modifications, and those modifications just simply mean shared means we share the weights between these visual encoders. Augmentation means we change slightly the images the sender sees versus the image the receiver sees. And they also show, okay, we are not only distinguishing concepts that we see in the training data, but also just pick out of distribution images, like things that are never seen in during training. And even there, the agents were able to communicate about this kind of out of distribution stuff. And the problem I talked previously that agents also just use this communication protocol to talk about random noise. This thing seems to be solved a little bit or quite a lot by using data augmentations, so that the sender sees a slightly different image than the receiver by perturbing, cropping, and etc. Yeah, and here you can see like what those symbols that the agents were communicating about really refer to. And you can see some, those are the 9 most frequent symbols used and what kind of images they were referring to. So you can see somehow this kind of thing, symbols are semantically relevant. And this is not shown here, but they also compared it to this unsupervised or self-supervised representation learning approach called SimClear. And they showed that, okay, we actually achieve quite similar representations if we use it on image classifier compared to this self-supervised approach, which makes sense because it's quite similar. And now to something more recent. And here the field diverges a little bit from this emergent approach. And look how neural networks or more language models would communicate with each other, not with random symbols that the agents need to find out, but with natural language. And this is one of those approaches. So basically, you have a lot of large language models and multimodal models, and they are trained on different things. So, for example, CLIP might be trained on image captions, but like GPT was trained on a lot of text data. And then you also have those audio language models that are trained on audio. And then you ask yourself, okay, how can they share their knowledge? Each one is kind of an expert in itself, and how can they share their knowledge to solve a common task? And they thought, okay, we don't want to train it, but maybe we just let them talk to each other. And this is what this paper investigated, how those large language models can talk with each other. And basically, it's nothing really complicated. Talking means just that they kind of, you just chain those models after one another. And in addition to using a prompt template. So I show you how it works in this example of image capturing. So you would first have a vision language model that gets an image. And this would detect the number of people, the places, the objects in that image. And you would have this template, which maybe some programmer defined. And you would fill those things that you have detected and use it as an input to a large language model. And just prompt it, okay, can you give me a caption for this? And give a caption, and then you can use again a vision language model to rank those captions. And then you have this finalized caption. And you can see it's quite verbose and talks about much more stuff than a normal standard caption model at that time. I think it's also quite nice to build applications. They showed this kind of possible product you can build, and it's about egocentric perception. So basically, what you can do is, okay, you just firm your ego perspective throughout your day, and you might want to ask the models, okay, what did I do today, or can you summarize my activities today? Or you can ask him, okay, what did I eat? And this is achieved by, again, chaining those vision language models with language models and etc. So to be more precise, you might have recorded this your daily life and you sample some video frames and you let this vision language model and language model go up to generate captions for those singular video frames. And so those singular video frames, they kind of describe a history, a log history of your day. And then this is basically can act as an input to another language model, which you can use to summarize your day or query what happened. Yeah, so for me, my thoughts about that workshop was, I think it was quite interesting because you don't hear it a lot. This is not a very popular topic, thinking about how neural networks would communicate with each other. And but I found that so there were some problems what I saw, like if neural networks develop some communication protocol, it's really difficult to decipher it and see what actually happens there. And how do you like find out is there a grammar that is similar to what humans use? And I also found it a bit surprising, or I don't know how to feel about it, that it's so similar to representation learning. So in the end, what is the difference between the matrix as a message that they exchange to a matrix like a representation that they exchange? And I didn't really figure it out. And also what I didn't really like is that the field is moving towards communication using natural language instead of like finding out like how language emerges, like what I would expect under this field. And with that, I want to ask you if you have any questions. Yeah.
Everything before the 2023 paper just seems like it was the same problems that regular machine learning had. Like, you know, the cow on a beach example, where like, what animal is this? Is it a cow? And then you realize, I was just focusing on the green background, and then you put it on a beach, and it's like, it gets confused, thinks it's something else. Yeah, and then like, as you mentioned, the representation learning kind of fixed that, but that happened in parallel fields anyway with like just on ImageNet or something. And then now we have the like semi-supervised stuff, which I don't think you touched on, but I guess it would just also improve this in the same way. Yeah, so yes, everything until the 2023 part just seemed like the reason why it was sort of failing was for the same reasons that, you know, more traditional problems were underperforming until they introduced this representation learning and semi-supervised learning. So it's just a thought, like.
Yeah, I don't know if I wouldn't say it was failing beforehand. Actually, I mean,
failing, but like
those symbols that they use to exchange messages, they kind of worked, even so they had this problem with the Gaussian noise. Still, I would say it was insightful to see how networks communicate. I mean,
yeah, but like if you did the latent space analysis like ResNet from 2017, it would also give this embedding probably. But then if you looked at like adversarial examples, you'd realize you'd have the same problem as the Gaussian thing. So it's not failing, it's just like, I think in parallel, like the more conventional problems, the more conventional things, apart from this communication problem, like the solutions kind of just apply the same.
Yeah, sure. Yeah, I mean, yeah, from what I understand, I guess, yeah, I mean, surely it will benefit from better architectures, better models. Is that what you mean?
No, but it's like,
like say if you do like masked auto encoding and then you sort of analyze images, if you, like this is a bit off topic, but it's like you can see where it's getting the semantic information from. Like if you have a picture of like the cow on a beach, you'd be able to like analyze it. So it's getting semantic information from the cow and not the green pasture in the background. And that comes from like having a different problem set up with the masked auto encoding. And like applying the same thing here would mean that you don't get this like Gaussian blob problem, right? But the point is that like separately independent of this like communication problem, they kind of solve this problem. Does that make sense?
What's the question?
Well, but if I may,
Yeah, sure.
that here on your last comment, because this could have been one of my question actually. So the Gaussian problem, which I find like really interesting. You mentioned, if I remember correctly, that okay, if it can solve the Gaussian problem, it probably means it has symbols which analyze each and every pixel, right? But could it be that it's actually rather that the message, right, to communicate this Gaussian is just like super complicated and something that so it's a very unusual combination, right? So imagine if we could interpret it, actually the network says at this time, yeah, look, it's a mouse who is eating an elephant on top of the Eiffel Tower, which is on the moon, right? Which is not the kind of thing you would see in an image. But this intersection of weird concept and very unusual intersection allows them to describe this kind of. So I think it connects a bit towards your question, if I got it correctly.
Yeah, I think I haven't read these papers, but I don't know how they. Like if you do like semantic image segmentation, you give like an option to predict like background. Like I don't know if because you have to hard select a thing that it's just the architecture having to hard select like something for the Gaussian noise. But I haven't read it, so I don't know. Do you know?
They hard select.
Yeah, because you don't. If you have like a vocabulary, you're asking it to pick one of these things in the vocabulary.
Yeah.
Like say in image segmentation, you have the option of like background instead of like predicting like cat or dog or whatever. Like, is there any like background thing they can, if you have to hard select something from your vocabulary, or if you, because if everything in your vocabulary is something meaningful and you haven't given like the background option, like then of course it's going to like give you something.
It will give you something, but if you get a random Gaussian noise like from the receiver and it wants to send this, the sender gets this Gaussian noise and wants to send something. Of course, it will need to send something, but the receiver might not be able to decipher it. So, but I mean, the problem is not that it sends something. The problem is that they can actually like have a successful communication. Makes sense.
Yeah.
Regards to what was mentioned before about maybe the string being super complex and actually explaining the actual noise, I'm wondering if that is the case, then maybe this whole experiment defies a bit the purpose of the task, because it explains a continuous signal with some other signal. It's different from what they want to achieve here, which is to probably the agents figure out something that looks like a language, so something that describes discrete symbols that are finite in the sentence. I don't know, I was just thinking about that when we were talking, that maybe graded like that. It's a different problem that we are examining, but a different setup.
So I totally get your point, and I think and I was really interested in really trying to understand how can it be that it can solve this task. And now so I don't know, but if I had to communicate with you take the left one or this Gaussian noise, I think I would have to write in my message to you. You have like 3 of this Gaussian noise to tell you, like, take the one with these kind of. I mean, I would not even know how to tell you which one to choose if I had 3 already these 2. And this is why I thought, yeah, maybe the ghost was super long. But I don't know how it goes. But I agree, it's not the purpose of.
But it's a very interesting case, right? Very interesting thought.
So I guess maybe it helps to know that. So you think about communication protocols that just construct a whole sentence. They're just picking a symbol from the vocabulary. It's just one symbol. So you can't get really, really complex.
Okay.
Could it just be detecting, like, does it return the same? I'm not sure if I understand this. It like given the left one, it returns the right one.
Great. No, so they solve this problem if you get those 2 blobs and they look different, and the sender gets this left one as a target, then the receiver can actually distinguish and pick the left one. And this seemingly shows that they use those symbols they are using might not need to encode something meaningful. Note that they have been trained on a real game where they play to distinguish between real-world concepts. And then at test time, they play around with the Gaussian images and still do quite well.
But what defines successful communication in this actually?
Yeah, so basically the sender will get like the left one or the right one, and it's random, and he needs to communicate this to the receiver. And it's successful if the receiver picks the target image.
All right.
But the message is kind of short, right? So there's some need for some form of compression, right? Like hopefully for natural images, we would compress it in a way that overlaps with human understanding, right? But to solve this, there still needs to be. Like my question is why? I'm not sure, like what this shows. Like what is the problem? That the concepts that it learns are not aligned with the visual.
Yeah, so we have trained this on, like, we have seen previously that we initially assumed that those symbols can actually distinguish real-world concepts. Mm-hmm. And maybe if I use those blue symbols, I can really say it's an alligator instead of a bomb. So that's what those Lazaridou did initially, and they thought, okay, cool, it works, and those symbols mean something. And
okay, I get it.
Those people tried it again. They trained it the same way as these people, but at test time they used those noise blobs.
Mm-hmm. But like, why would we expect that to happen in the first place, right? Like, if you solve a classification problem, then like it makes sense to kind of embed all dogs next to each other, right? But if you solve this problem, like you might as well just focus on like say these pixels are blue, then you pick the left image and so on, right? So like there's nothing in the task, right, that would enforce this kind of embedding.
Yeah, that's what I meant by the background thing. Like if you're doing segmentation and you're saying like color the dog good color, the model has an option to say the background is the background, and then if you give a picture that's empty, it will just say it's all background and you don't care. Like, but in this, if you don't do this and you just pass noise, it will still predict something. So what would you actually expect to happen if it did learn something? Like if there's no like background or nothing option. Well, it's not like some Bayesian ML thing where you can be like, I'm not sure. Like what do you expect to happen?
Under this noise game, that they fail basically. The receiver can't distinguish because message they send is kind of undecipherable.
So when it's training and at the start and both of them are not trained, it's just kind of like guessing.
Yeah.
It's still guessing Spanner or Margarita, whatever it was.
Yeah.
But it's not saying you don't want anything, or I don't know. Is it? Like, what's the background?
There's no background. You pick something.
But does it have an option to say I don't know or nothing?
No. You pick something because there's always actually a right image the receiver has. Among those candidates, there's always the right image. So there's always the correct answer.
I think in the interest of time,
Okay, sorry.
Move on because we have a lot of people to talk about.
Yeah. I'll hand over to my wonderful.
Thank you so much. Yeah, maybe let's do a 1 minute break and reassemble it. So we can we're gonna open the window.
Cover it right now.
It's like just
Let's see.
Yeah.
Should I try it today?
Yeah.
Here.
it was like if it doesn't have the answer, it's going to give something. So if you give it, it's like giving the class.
Yeah.
Oh, thank you. You give it a picture of you now. So my question like there are architectures where they decide. But I think it's maybe a little.
Totally understand the idea. You want to think, don't make coding. And yeah, somewhat depends on there's not the concept that I believe my capture. But and here it's just a really guaranteeing.
Maybe it's not feeling we're framing.
It's just existing that way that we don't cannot capture right now.
So you're like telling it to give an answer when you really want to listen.
And then we got in the experiment.
No. Oh, you are almost running out of 4% battery.
Did you give Stein Gaussian language objects like cat? I think I need to read it like to see exactly.
Roger, incoming. I think then we're ready to call our next speaker. Maria is also an engineer in our team and forward to your favorite papers.
So, welcome from me as well, everyone. I had chosen 2 papers to present that made a big impact on me, but maybe for the interest of time and to give some room for Tanya to also present her highlights, I can present one of those, and later on the slides I think are going to be available, so you can check the other paper from the slides. So the paper that I'm going to present to you is titled "What Makes Instruction Learning Hard? An Investigation into New Challenge in a Synthetic Environment." Okay. And the motivation behind this paper is that in the traditional setup of machine learning, we have a model and we update the model weights so that the model learns to perform a specific task. But in instruction learning, the setup is different. So in instruction learning, a model learns to perform the new tasks by just looking at the description of the task. So maybe you've heard of one example, FLAN-T5 is one model that does instruction learning and has become quite popular. But the expectation, what we want to do with these models is that we would like to give them some input in English. So, for example, we would like to give the network an instruction and a review. Just write it in plain English, natural language, tell me whether this review is positive. The review is this movie was a waste of time. And the model is expected to, first of all, understand English, interpret the instruction that we give it to it, and then also execute what we asked it to do. But the question that the authors pose is if actually large language models can become good instruction learners. And they say that in previous work, people look in the domain of natural language, but this is a bit problematic. And the reason is that natural language is very complex. So in that case, it's hard for us to understand and analyze what type of instructions models can actually learn and what expectations we should actually have from models that are trained on instruction learning. And they propose a solution for that. They developed a synthetic task, and instead of using natural language, they suggest that we can use regular languages as a proxy for natural languages. So, high overview of regular languages and regular expressions, because this is not a topic that's very involved in the day-to-day work of machine learning engineers. I personally had forgotten a few things from when I was in the university. It was a good opportunity to remind myself. So regular languages are a type of formal languages, and a formal language is a set of strings that a set of strings of symbols, symbols that come from an alphabet. So, for example, the set of strings that contain A is a formal language. And regular languages are a subset of formal languages that share some common properties, and they have been studied in great details. So they advocate that if we work with regular languages, we're going to have the advantage that we're going to have a setup for making experiments in a controlled environment, and the known properties of regular languages will allow us to make hypotheses about what we can expect from the models. And regular expressions are used to describe regular languages with just using a few symbols. So, for example, a regular language that has strings that contain A would be very large to describe if we enumerate all the numbers in the set of the language.
So we can equivalently describe it with just using A star. So this A star is the regex that describes this set that is the regular language. So they say that instruction learning can be framed as a problem in general as a higher order function. So a function that given an instruction language R returns another function that maps X to Y, inputs to outputs. And in the natural language setup, like the example that we saw before that was in English, the instruction language is English. The input space would be the string that we provided to the network. So the move review, and the output space would be some classification of if the review is positive or negative. So when we try to make a similar adaptation for the case of working with regular languages, the input again would be the instruction language, but in this case it would be a regular expression. Along with that, we would give as input a string, and the model would have to create an output that would be true if the string belongs to the language that the regular expression describes. Maybe it will become clearer when we see an example from the data set that we created. So for doing training and evaluation, they used the by T5 model large, and the choice was very specific. They wanted to use a model that uses character level tokenization because they had such a synthetic environment, such a synthetic data set, that if they would use some other model that does some word tokenization, that would probably not work well for their inputs. And regarding the evaluation, they mentioned that using raw accuracy can be misleading because a model might appear to do well on regexes, but it might be missing edge cases that are actually very important. So instead of using raw accuracy, they measure the proportion of instructions that the model can learn very, very well. So they measure for which languages the model becomes very fluent in a sense. And these are regexes for which they achieve an accuracy that is over 90%. And then they analyze the effect of language level attributes, regex specific attributes, and input specific attributes. So language level attributes are the ones that have to do with the regular language that they're examining. The first attribute that they check is star-free and non-star-free languages. So non-star-free languages can account for languages that have to do some modular counting. These are languages that need to keep track of some quantity. For example, in a language like that, if I describe what this means, is this language is the language that has an even number of A's. So if you want to check if a string belongs to that language, you actually need to count how many A's you've seen, if the number is even or odd. And they plot the accuracy. So the blue line is the mean accuracy. And they see that the mean accuracy is longer for non-star-free languages compared to star-free languages. And here, using the metric that we described before, they see that the model can learn with a very high accuracy 91% of the star-free languages, but only 72% of non-star-free languages. So they make a claim that since in this setup the model structures, the model struggles with non-star-free languages, then we can generalize this and say that in general we should expect transformers to also struggle with following instructions that require counting. The next attribute that they look at is language size. So language size is how many strings a language contains. And there can be languages that contain an infinite number of strings. So this one here that we saw before is a language that contains an infinite number of strings. For those languages, they only consider strings that have up to 15 symbols of length. And again, when they plot the accuracy, they see that the accuracy is decreasing as the size of the language becomes bigger and bigger. And for evaluating their accuracy metric, they consider as small languages that have less than 64 strings, and as large languages that contain more than 64 strings. And yeah, there's a big difference between those. So in this experiment, the intuition is that more ambiguous instructions are ones that might be executed in multiple ways. So if we translate that in such a setup, it would be analogous to having a language with many strings. So to express the same thing, you have different options. To express the same language, you have different strings. So from this experiment, they claim that precise instruction with few possible interpretations are easier for transformers, and more ambiguous instructions are more challenging. So basically, the more expressive a language is, the more a language has different ways in which you can express the same meaning, the harder it is for transformers to learn to follow instructions in this language. Next, they look at an expression level attribute. So this has to do with the regex expression itself they're using, and this is composition. So regexes are composed of smaller regexes. For example, this regex has 4 compositions because it has 1 star, 1 union, and 2 concatenations to create it. And they look at how this affects the accuracy. So the mean accuracy decreases as the number of composition increases, but this effect is much smaller than the previous ones. And the next attribute that they look at is unobserved local structures. So regexes can contain sub-expressions. These sub-expressions are called local structures. So, for example, this regex A or BBA, many times repeated one after the other, contains the sub-expression A or BBA, which in turn contains the sub-expression BBA, which contains the sub-expression B. And some previous work had mentioned that transformers find it hard to generalize to examples if they contain substructures that were not seen during training, so that they were not present in the training set. So to test this, they extracted all the regexes and their sub-expressions, and they controlled for this. So they classified the regexes by whether or not they contained sub-expressions that were absent from the training set or not. And they actually tried to see if this hypothesis is true. So the hypothesis that was made in the previous work is that if the model has not seen a sub-expression, then that regex that has the sub-expression would be harder for the model to learn. And the previous work was looking at all the regexes together. And when you look at all the regexes together, it appears that with unseen data, actually, the accuracy drops. But now that they had also controlled for the seen and unseen regexes on account to number of compositions that they have, they see that the effect actually disappears or it even reverses. So in this case, the accuracy for regexes that contain unseen structure is higher than the seen. And they claim that the previous hypothesis was actually wrong. And this is a case of Simpson's paradox. And this is a paradox where the relationship appears when you look at the data in aggregate, but when you control for another variable, the effect reverses. Instance level attributes are the ones that have to do with the input, the specific input that they give to the model. And they looked at the execution states. And for its language, they constructed the minimal deterministic finite automaton. So this is one way that you can check if you have a string and a language, if that string belongs to that language or not. You create the automaton and you try to parse that string through the automaton, then go from state to state according to what you see in the input. And if you reach final states, it means that it belongs to the language. So they did that, and they tracked the number of states that were visited while trying to recognize the strings. And they saw that instances that required many more execution states to be visited in order to pass that string are harder for the model to learn to recognize correctly. And the intuition of that phenomenon that they see here in the natural language setup would be that visiting more states means that you need to take more context into account when you make your decisions about what state you want to visit next. So they claim that transformers will have difficulty following instructions when they have to closely track context in the instructions. So in conclusion, regexes are a very useful proxy for instruction learning. They allow them to have a control setting to do the experiments. Models are not good at modular counting ambiguous instructions and context-dependent tasks, but they say that there are probably a lot more other factors that have not been shown yet. And that's why the dataset that they created for this paper is publicly available, and I encourage everyone to play around with it. And the final thing that you can find more details about it in the paper is that they also retrained on the subset of examples that were the hardest ones for the model, because they wanted to see if the model actually performs badly in these examples because it actually cannot learn them, or the model performs badly in these examples because they are just underrepresented in the data set. And their findings were similar. So these experiments also further supported their case. And that concludes the presentation. We can now discuss and ask questions.
Thank you for the presentation. Very interesting. One thing I didn't quite understand is how. So we use these regex languages, right? How do you tell a model a task with such a regex language? How do you yourself know what this how do you translate from describe the review of this movie into a regex language? So this was something I didn't understand.
Yeah, because the regex is expressing the language, and in the other case, it's a bit confusing also for me when I was reading the paper, because basically the way that they define it here is that the input is the instruction language, and the other input is a string. So here they give us input the regex, and the other input is again a string. But when we look at examples in natural language, the first instruction is not some string that represents English, right? It's just an English sentence. It's not some input feature that determines English, or a tag that says English, so understand English. So this is a tricky part that I was also thinking about when I was reading the paper, because it was confusing, and I think it might be a leap of logic there.
So they translated these English expressions with the same rules into regex languages?
No, they don't use any natural language. I think there was a slide here with a data set. Sorry. So it was in the unseen. I think this will clear up some questions. That's what they use. That's the data set they created. Sorry for that. I think last minute I removed it because we were running sort of out of time. But actually looking at the data set, I think it's very important because they use a synthetic data set, and it's hard to understand what they were doing if you don't look at it. So they created this data set. It has train and test set, and these two are the strings that they give us input, and it's the regex and the string, and the model has to predict true or false if this string can be expressed by this regex.
I had another question. This cleared it up already. So I was wondering what the setup is. So they take this T5 model, and then they fine tune on a training set, and then they test.
Yeah.
Okay, so they don't take just a language.
Yeah, exactly. They don't use natural language at all. That's why they always mention the intuition that they use, and try to better emphasize why they think that this very abstract conclusion that they see, this very abstract observation that they have in this setup, could actually be something that would also appear in a natural language, because they just use this very synthetic abstract thing. And just to say maybe an example from here. So if I express in natural language, this first regex, it would be the language that contains all strings that have some A's in a row, and the last character is B. So if we look at the string AAA, this string cannot have come from this language because it does not end with B. So the output of the network should be false. But this second one could have come because it's AAB, it ends with B. Another string that would have come from this language would be AAAAAAB.
To me, it seems like the binary problem is like the wrong way to do this. Because if you just had it like an autoregressive model, and then you did like, you sampled it, like if you sample it at a probability, sometimes AAB will come up and sometimes AAAB will come up, right? Like, because it'd be a probability, if you do AA, then the probability that the next one is B would be like some probability that would decrease as it goes on. But that actually wasn't my question. My question was, how did they do the task where they tried to get all the sub instructions? Because you said there was one like A, B star would be the same as breaking it up into smaller regex. But how did they do that? Like there was a slide that said to test the hypothesis, they wanted to see if there were certain regexes that could be all the sub expressions. Like, how did they do this test then? Like, how do you get the sub expressions from the prediction?
I think the prediction is true or false.
Yeah.
So this is they split their data for training.
Yeah.
And
so when you classify, so the second point there, classify all the regexes by whether or not they contain sub-expressions. Like, how do you do this analysis then? So you have your model, and then you would have to know what the sub-expressions were, and
maybe the thing that's confusing here is that they use classified. That just means that they did different experiments. So maybe instead of classified, say they split all the regexes in the training data set into two groups. One group had from the test set, sorry.
Yeah.
They look at the test set and they find the test set the examples that have a sub part that was never seen during training. So this is one group, and the other one is the other.
Yeah.
And also, like, for what you were suggesting before is very, very interesting. It could be a very interesting future work, but it actually, the reason why they have this binary setup is because here they try to make the claims. What you are suggesting with an autoregressive model would be like a language generation model for these synthetic expressions, right? With the autoregression.
Because then you could sample the top probabilities, and then probably if you sample like the top K5, you would get these sub expressions, but it might be less character efficient.
Yeah, I see your point.
I don't know. Do it.
But yeah, I believe there are some non-machine learning, more standard ways that you can see, like mathematically, these regex, you can get this regex and have something provide all the strings that can come out of this regex, but like maybe it would be interesting to try to do it with machine learning and see if I can have an autoregressive model produce all the strings that can come from this. Sorry, it's just thinking.
How many samples are in the dataset?
I don't know. I don't know the size of the
Also,
dataset.
not how many different instructions they have, because you have like repeated instructions.
Yeah, I don't know this detail, sorry. But I think I looked at it briefly and it was not such a big data set.
Because they start with a model that was trained on natural language. Then they,
No,
okay,
no.
so it was randomly.
There was never natural language. That's the
It was
whole idea.
randomly initialized.
No.
So
So
it was
the
one.
whole idea that their whole idea is that it's very hard to do this when we work with natural language examples.
Yeah.
That's what other people are trying to do. And they try to find connections in semantics or morphology or whatever. So they say, don't look at natural language, that's such a hard problem. Try to see how models can solve problems in a synthetic environment with these regexes. And the conclusions that you make, you can generalize them for natural languages because the properties.
Yeah, but they fine tune a model with this data set. So they start with some model that was pre-trained or it was randomly initialized. And then just train it. Like I think it's at the beginning,
yeah.
they start with sample model. So that divides training natural language.
Okay. Yeah, you have a point there.
So it has to be a large data set. So the model kind of forgets natural language and try to think
Yeah.
so formally to be able to give proper results.
I understand your point. I'm not exactly how by T5 was trained. So you're right.
You randomly initialize, I guess, but you would need like probably a very large synthetic data set.
Yeah. So I don't know how by T5 was trained, but I totally agree with you because if this was pre-trained on natural language and you just like now give it these strings, it's
asking to act very formally with all these regular expressions.
yeah, and it has already learned information from pre-training on natural language, and now the task is easier for it. Yeah.
And on the other side, if you would start with a random model,
Yeah.
then just training it on these regular expressions would be very different from how transformers are trained.
But it's probably easier, no?
Yeah.
To train so with
But-
formal synthetic data set.
But what I mean is making claims back about the land.
Yeah, that totally makes sense.
It's
Yeah.
totally different training.
Yes.
Because they probably don't use any kind of masking.
So yeah, I hope you found the paper interesting. Thank you very much. And now I will welcome Tanya to give the final presentation.
So I think I have like 12 minutes. Yeah, good news, I have like very much easier papers. I think like they're like much more applied machine learning and like not so theoretical. So I have 3, but I think I'll like try to do 2, like very, very high level. Yeah, so the first paper was in the interpretability track. And yeah, basically they are trying to use contrastive explanations for language models. And yeah, this paper got an honorable mention at the conference. Yeah, so we're talking language model, right? So we're talking like predicting next token. And like basically we have some methods, like gradient-based methods of explaining like decisions models make. But for language models, it's kind of tricky because like you have so many tokens you can predict, right? So like usually you would have like 5 classes. Okay, you look at your class, you like backpropagate, but here you have like a space of so many decisions. And another thing is apparently if you use standard methods, quite often it would like say that the most important token is the last one before your prediction, which kind of makes sense because like, yeah, your last token tells you like, okay, probably you need to have a verb like next, but that's not what we as humans think about. Like that's good, but that's not what we want to see probably. So here they work with this example. Like basically the question is like, can you stop the dog from? And the output is barking. So with the standard methods, you would say that the last token is most important because you need the verb, you need like an in the end, and like that's it. Yeah, and they basically say that using contrastive methods, which I will, like it's very easy, I will explain in the next slide. You don't ask the model what is the next token and why, but you ask like, why is this token better as another one? So for example, here, if we ask like why we choose barking over crying, then we probably want to attend to dog. Like we will probably want to say that like dog is the important words because like dogs are rather barking than crying. That's like more common verb that dogs do. But if we ask like why you predict barking instead of walking, then probably you want to like pay more attention to stop because like why would you mind the dog walking? Like that doesn't make sense, right? But like if your dog barks a lot, like you want it to stop. So that's the idea. Yeah, and basically they do a very simple thing. So normally you would have like a gradient of your like logit for the predicted output, and you like calculate this gradient with respect to all inputs, or you have like inputs times gradient, and there are like more papers, more methods in the paper also. And all they do here is instead of just taking a gradient of the logit, they basically take like two logits for the predicted token and for the one you want to compare it to, and they just take a difference. And they just substitute it. So like that's as simple as that. Yeah, and they get kind of nice results. So like first of all, you can see here that this contrastive gradient method like outperforms other methods, like including not contrastive ones. So this is nice. And another nice quality that it has is if you, so here you have an example of general relativity predicts the existence of, and you would expect the next word to be black. And then you look in different types of words you could use as the next one. For example, you give like red or yellow, or you give like English or Asian. And the nice thing about it that like red and yellow like cluster together, and English and Asian also cluster together. So that's like a nice property to have. That's something you would expect that like if you like look at the colors, you probably want to like look at this token to explain it. If you look at some other things, maybe to some other, and you can kind of like think about it a bit further, right? Because like maybe you don't have just one token, but you just have some kind of like, let's say it's distribution, even though it's not a real distribution, right? But like, and then you can say it's kind of similar and it's a nice property to have. Yeah. Read the paper, there is much more in there. That's just the basic idea. They also conduct experiments of like showing this explanation to humans, and humans prefer the contrastive explanations. It makes more sense to them than the non-contrastive ones. So yeah, just an idea. Look into it if you're interested. And do you have any questions to this?
I'm not sure if I understood the last example you gave there with the general relativity predicts the existence of black. Like,
yeah.
Why? What's this black?
I'm not a physicist. I would imagine it's black. Yeah.
Okay. Cool.
Is there a I mean, I would also do that, but why do you look at the gradients at the last layer? Like, is there any insight to be gained not looking at the gradients at the last layer?
You do look at the gradients of the last.
I'm saying, like, is there any reason why you might not want to do this? And would it tell you anything?
Where would you look instead?
And not the last.
But like at the last layer, you have like actual like classifier kind of, right, for your last token, for your next token, right? And then you have like probabilities over possible tokens.
But it's the same with like language models. You might say like early layers have like lower level features, like edges or something.
But how you would attribute lower level activations to the predicted token?
Yeah, like, so I don't know much about this field.
Or do you mean like the ones? Okay.
Is there an analogy? Like,
but do you mean like which one you call the last and which one you call the first? So the last is the last before logits, or the last is the. Okay, but then so I think like it makes sense to look because like that's where your information of what you choose is. Right?
Yeah, so I would also pick this, but the question is more like this: is there an analogy between, in the same way with images on early layers? closer to the input, that like there's a different sort of like semantic.
I think the difference is so for images you also have similar interpretability methods, right? Like GradCam, where you also look at the last layer before the classification, and then you show which parts of the image are most important for classifying this class, which is very similar to this one actually, where you show which parts of the sentence are important for classifying this next word. And but you also get what you just were talking about was you could look at the early layers and show what kinds of features they extract.
So,
and maybe you could, in this way, you could maybe extract word relations or like visualize word relations, right?
but that's not the task.
So basically,
something
we
different.
know from previous work that in the layers of the transformer, in the beginning, the information that is encoded is very low level. So in the first layers, it encodes things like morphology and syntax and grammar. And in the layers that are near the output, it actually, it's very, very analogous to the visual computer vision case. In the layers near the end, near the prediction is where it looks at the example specific structures.
Yeah, so then
So
given that, is there an analogy to this gradient thing looking at early layers?
good, but here they want to look for word meaning levels. They want to distinguish according to the meaning of the two labels, and this is happening in the later state, in the later layers. But if, for example, they wanted different, they wanted to choose if the next token, for example, is going to be a verb or a noun, then they would do the same thing, but they would look in the layers that are in the first layers of the transformer.
Yeah, so that answers
Okay. I'll try to squeeze in one more paper.
I think we don't need to like rush it so much, but yeah, maybe
Okay, I can do it.
some people find with some more.
I'll
Yeah.
skip.
Okay.
Okay. Yeah, so this paper was from the industry track, which I think might have been the first year that they introduced the industry track, which is like, I find very interesting also for us as a company, because we work in industry, like we also do research, but like as engineers, we work in industry. And this paper is from Amazon, and it's about knowledge distillation for natural language understanding. Yeah, so here's like their slide for motivation, but basically the idea is like we have now language models, they're large, they're everywhere. But if you're Amazon and you have Alexa, like you can't deploy your large language model on Alexa, and you have like this kind of like, you want low latency for your system. So we need like some ways to deal with it. And they say like knowledge distillation is like one of the things that are made especially for this, right? Like to kind of like transfer from like bigger model to a smaller model. And the question they ask is, okay, like large language models are pre-trained on like very general language. And your downstream task probably is very different from this. Like, for example, for Alexa, you need to like understand commands and like execute, like make sense of these commands. So the question is, they ask is like, how should you distill from a larger model to a smaller model? And yeah, so basically what they mean of how to distill is you have your like data set, they call generic data that the big model is pre-trained on. Then you have your task-specific data. And should you distill just on the generic data? Because that's actually what your big model is trained on. So you probably have like some nice activations from there. Should you pre-train on your task-specific data, even though it might be very different from what the model was pre-trained on? And so like your activations are kind of like more noisy compared to the original data. Or should you maybe pre-train on some, should you maybe distill on some mixture of both? So yeah, this looks a bit scary, but it's actually very easy. So basically they use several scenarios. They use two baseline So one baseline would be like not use any distillation and just train the small model like on the generic data, because it's a big enough data set, you can just train on it. Second baseline they use is distill also just on the big generic data. So these are two baselines. And then they conduct like two groups of experiments. So one is like there's no fine tuning, and you kind of mix the generic data and the task specific data in a 7:3 ratio, and you distill on this mixture. And the second one is you distill just on your target data set. So you don't use the data the big model was pre-trained on for distillation at all. And the second group of experiments is like, if you have, like, if you're big enough, like Amazon, maybe you can fine tune your large model also first before distillation. And you can also fine tune it on a mixture. You can fine tune it on the target data set, and then you can distill it. Okay. Yeah, so here they just basically talk about metrics. Like it's the same, upper part is the same, just the lower part is about metrics. So they have two tasks that are interesting for them. And here DC stands for domain classification. So I think it's like if it's books, if it's about music, if it's about like basically what domain is it about. And the second one is like intent classification named entity recognition. So for example, if it tells you like the user says like play this song, then like play is intent and you need to classify this intent. And then the song name is like a named entity. And yeah, so for domain classification, they just use an F1 score and they compare F1 score from all these experimental setups to the baseline. And yeah, like this is like some metric for like this intent classification named entity recognition. Like there's details in the paper, it's not too complicated, but that's just a metric to use for this. Yeah, and basically here are the results. So at the top, we have this domain classification. At the bottom, we have this intent classification named entity recognition. And the test set is the test set, and tail test is just like subset of a test set that just like has like very rare examples. And basically, yeah, the learning here is that always distill on task specific only. Like even though this like embeddings might be noisy from your teacher model because like this was not trained on it, it's better to use this for distillation. Yeah, and in most cases, if you have the capacity to also fine tune the teacher first, then first fine tune the teacher on your target data set and then distill only on the target data set, with like one exception here of Spanish. Yeah, which I mean, right, like we're talking industry, so just like it's their specific use case, it's like what worked for them. I don't know how well you can like generalize it to like all other problems, but like I found it very interesting because like it's something as like a company that like works with industry partners, you like have a lot like, okay, we have large language models, like what now? Yeah, so any questions on this? Okay, cool.
And once of distillation, then everyone has compute power.
Yes, Maria will give some final thoughts.
So some quick final thoughts that I had when visiting at the conference. One thing that, well, first of all, it was an amazing experience, of course, and it was a very great opportunity to see what's happening in the field. I met a lot of great people and had very, very interesting discussions. Regarding the work that was presented in the conference, my personal feeling was that there were a lot of papers that had to do with creating new benchmarks and evaluation metrics. But I also have here a slide that shows the submissions according to the tracks of the subcategory, the conference, the topic that they were submitted to. And this is a slide that was presented at the opening ceremony. And In the top place, most papers submitted this year had to do with the topic of information extraction. And dialogue and interactive systems are a topic. It's in the third place, but actually there has been an increasing interest in the last years, and they are catching up very fast. So maybe next year they're going to be the topic that has the most submitted papers. Another topic that's actually getting a lot of interest lately is multimodality and grounding. And the best paper award was given to a paper that was actually in that area. It was very interesting. I would encourage you to look it up. It was about creating a data set with some abstract shapes that are called tangrams. And they have included a lot of features in that data set. And they hope that this is going to help with experiments that work in a multimodal, so language and vision, and a grounded way. And the people in the community are the least interested in discourse, syntax, phonology, and all like the classic linguistic stuff. So it feels like in the beginning, computational linguistics and NLP were the same field, but lately NLP has been diverging and it's becoming something completely different from computational linguistics. It's a new field on its own. And I will close with this demo. So it's a very interesting demo. You can scan and check, it's online. There was another similar one, but unfortunately it's not online. So in this paper, they created embedding representations for scientific papers. And they explained the method in the paper, but they also had a demo to solve. And they used the papers that were submitted in the conference on the demo. So they have an interactive map that you can use to navigate the papers that were submitted at EMNLP 2022. And papers are colored according to which track they were submitted to. And you can hover over the embedding space and see the title of the paper. You can click and see like the abstract of the paper, and you can also like search and find in the embedding space something that's going to be a paper that's going to have something similar to your search query. And thank you very much, everyone, for attending. Maybe Alex can.
Yeah, I think that's, we should give you another. Yeah, thank you so much, guys, for coming, and it's been really a pleasure to have you all here. Thank you again to our speakers, and yeah, I just wanted to say two things. So this really is an open stage, so if you are in the research domain, or if you have some research topics you want to talk about, then you can talk to me and present here at the paper reading group. So that's definitely an option if you guys are interested. And then also, yeah, this is a space to connect, so feel free to mingle and stick around for a little bit and get to know the Berlin machine learning community. Then, yeah, I wish you a lovely remainder of the evening and see you next time. Thank you.